So, good morning. Welcome to the classroom. Today we look at the inhomogeneous linear systems, because we have had a look at several aspects of the homogeneous linear system. Now we consider the problem of solving inhomogeneous linear systems. Okay, the non-homogeneous linear system is of the form PT. So we take this. This is in fact, if you write down in terms of the components, it is going to be dxi by dt equal to sigma 1 to n aij xj bit for t1. We are assuming that both, see, A is given by aij and B is essentially the column vector b1, b2, bn. They are all functions of t. We assume that these functions are aij's and bi's are continuous on these are the assumptions that you make. Now, one of the, we make use of our studies on the homogeneous system to solve the inhomogeneous system. The associated homogeneous system is now you know that under these conditions the solutions exist on this interval, throughout the interval t1 to t2 for a given initial data. So what we want to get is a general solution of this, so that we can get a particular solution, making it to satisfy a set of given initial conditions. Okay, so what do we know about this? Under these conditions, you know that there exists a set of n linearly independent solutions xn which forms a basis for the solution space of I call 1, 2. That is the homogeneous equation. Therefore, any general solution of 2 is given by xt equal to c1 x1 t where c1, c2 etc. cn are constants which is to be determined using the initial data, and you can determine them uniquely, because if you look at this one, suppose your xt naught equal to some x naught is the initial data, then what you have, you want to determine c1, c2 etc. cn such that xt naught is equal to x naught. So you end up with equations sigma cj xjt xjt naught equal to x naught. Which corresponds to n simultaneous linear equations for the components of this x1 to determine c1, c2 etc. cn. Okay, therefore what you get is, see, something like, let me write this, so you get something like this, xij t naught. Now I am writing the components acting over C. C is a vector C1, C2 etc. Cn. This is equal to x naught. This is an n by n matrix, and this is a column vector with the entries C1, C2 etc. Cn. X naught is given, and this you know already, and is it invertible? So the question is, C can be uniquely determined provided this equation can be uniquely solved for unique solutions, and that is possible because you see that, you can easily see that the determinant of this is not equal to 0. The reason being that the column vectors are x1, x2 etc. xn, they are linearly independent. Since this for the solution space, which in turn implies, and this you know is if and only if the vectors these are linearly independent, therefore the determinant of this is not equal to 0, therefore you can solve this uniquely for C1, C2 etc. Cn. So that is clear. Now we make some observations. Suppose y1t are two functions, two as solutions of the inhomogeneous or the non-homogeneous linear equation 1. Now you take xt, you define as okay, then you can easily see that what is dx by dt. First of all, xt is a solution of the, so what we are going to prove is that xt is a solution of the homogeneous equation, because what is this? This is equal to dy1 by dt and this is equal to a of ax. Therefore, if y1 and y2 are two solutions of the inhomogeneous or the non-homogeneous equation, then their difference is a solution of the homogeneous equation. So xt defined as the difference of two the associated linear homogeneous equation. Therefore, what can you say about what is the difference? See, you can obtain y1 plus y1 from y2 by adding to xt some solution of the inhomogeneous equation. Okay, therefore the problem of solving, see, once you have solved the associated linear system and you have found a basis for the solution space, then solving the non-homogeneous system corresponds to actually getting some particular solution of the non-homogeneous equation. Okay, so any solution of a general solution of the non-homogeneous equation is the sum of a general equation of the associated homogeneous equation and a particular solution of the non-homogeneous equation. That means a solution of, say, yt is a solution of 1 if it is the sum of if yt is equal to xt plus some zt, where xt is a general solution of the associated homogeneous equation 2 and zt is a particular some solution of one. That is the observation that we make. See, from this what you have, see xt is now what you have, so yt is equal to sigma ci, which is which forms a basis for the solution space. So I equal to 1 to n plus zt. Therefore, what is that you need to work on? You have to find out C1, C2. See, once you know ZT, okay, then you can write down a general solution of the non-homogeneous equation as yt plus a linear combination yt equal to a linear combination of x1, x2, etc. xn plus z. Okay. Can you determine xt naught? Suppose yt naught is equal to, suppose the initial data for 1, that is the non-homogeneous equation, is y naught, that is yt naught, y naught. Now what do you do? It's easy to work on. So this is a known solution. Therefore, what you have, this is the equation that you have to solve. So what is it? See, y naught equal to, you want to determine C1, C2, etc. Cn such that y naught is equal to sigma I equal to 1 to n Ci T naught, Ci xi T naught plus Z T naught. So once Z is known, let us take Zt naught equal to, that you can compute, is Z naught. Then what do you get? You get sigma, Ci's are to be determined, oh sorry, it is y naught minus Now, can you solve this? Yes, you can solve this because you know x1, x2, etc. form a xn form a linearly independent set of solutions. Therefore, the vectors x1 t naught, x2 t naught, the above equation has a unique solution Therefore, this will give you then, with those CIs, this will give you a general solution of the non-homogeneous equation. So, our problem, once you have solved the homogeneous problem and found a basis for the solution space, then your problem for the corresponding non-homogeneous equation is to find some solution of the it's not, I mean, any particular solution would do. With that you can get the general solution, because all that you have to do is to solve this particular equation. Okay? So the problem reduces to how to find a particular solution of one. So this is the problem. How to find a particular solution of one. Can you use the non-homogeneous, the solution basis or the basis for solutions of the homogeneous system? That is something that is readily available in our hand to find a solution of the non-homogeneous equation. Let us explore this problem. Now you see that if CIs are taken as constants, then you see that a linear combination of x1, x2, etc., xn is a solution of the homogeneous equation. Okay? Therefore, what we do is, it's just almost sort of using your gut feeling that we vary these parameters, vary the parameters C1, C2, etc., Cn, in the sense that you take them as functions of t and then find out whether you can determine those functions of t. Okay? So the method is this. That means we have solved the homogeneous problem. Okay? Now assume Zt equal to C1t Now these are no more constants but functions of t. Okay? Now find out, is it possible to determine C1T such that is a solution of equation 1. So what do we have to do? See, we have to use the condition that it's a solution of the inhomogeneous equation. So let us simply substitute in that. Okay. So suppose I substitute in that, then what happens? I am substituting x equal to z. So what we want is dz by dt equal to a so what is dz by dt? Dz by dt is, we will have two portions. Okay. Because this is your z. So if you take each of these terms, then this is what you have. See, dz by dt will be sigma cit dx by dxi by dt plus sigma dci by dt xi. Okay, so this is I equal to so what do you get? Now you see xi t are solutions of the homogeneous problem. Okay, therefore see what is the equation that we want z to satisfy. So we want dz by dt, okay, therefore we want this sigma cit these are, you know, n scalar valued functions c1t, c2t, etc. cnt. Should be equal to at plus b. This is what you get. Now look at this. So this you get as CIT. You get dxi by dt minus this I move from that. Okay? Plus dt. This is what we get. Now what do you know? You know that this is xi's are solutions of the homogeneous equation, therefore each of this is 0. So this equation reduces to, which implies okay, let us write this down in terms of the components. In terms of the components, this is going to be xijt okay, it comes from there. This is what you get. Okay, can you solve this? Because these are known, and you know that xijt, determinant of xijt is not equal to 0 because they are linearly independent solution for any t. Okay, therefore you see that these matrices, this matrix that you have is invertible. Therefore what do you get? You get dc1 by dt dcn by dt is equal to so what do you get here? So this is equal to this, you can compute because this is a known function. It's a known matrix because you are writing down the inverse of this particular one, and this is something that is already given. Therefore what do you get? You can write this as you will get psi 1t, psi 2t, etc., psi n t. So I call this I define as psi 1t, psi 2t, etc., psi n t because these are functions of t. So what do you get? You get the following. Now I can take this out because I hope it is in your mind. So what one gets is first order equations of the form dci by dt psi. Okay. So if you want to call this column vector psi and this as b, then you see it is this inverse of this operator acting over b will give you psi. So this can be computed. So these are the equations, and you see that this is purely a function of t, a known function of t. Therefore, what is going to be CIT? Ci going to be integral d tau okay. So these are the constants that you evaluate. Sorry, these are the functions that you evaluate. Now you can use these functions to get the, so the general solution xt of is, these are constant I am writing, so this is I get plus Cn you can write down this is sigma this will be the general solution of therefore what we have done is we have varied the constants. The constants has been replaced by possible functions of t, and then try to determine those functions under the condition that the varied solution satisfies the non-homogeneous equation, and that can be determined by through a process of simple integration, and these functions can be determined. Once these functions are determined, you know this is a particular solution of the this is what is called, we used to call it the particular solution, particular integral of the problem, and this is what is called the general solution. Okay, so that is the structure that you have. Now you can quickly see some specific cases. I will give some example where you can actually work it out. I'll give a set of examples where you can work it out. So for instance, you can look at this equation. What is it? Say dx1 by dt this is a homogeneous equation. Okay. Now I will give this example for you to work out. To find out a general solution of this homogeneous equation. Then find a particular integral of where f1 and f2 are given functions, or if you want you can use the same notation. Once you get the general solution of this, then you see the computation of a particular integral or a particular solution can be done using this method. So I hope you have understood what is the how you actually compute these solutions. Okay. So what happens if bi's are all 0? Bi's are all 0 means psi i's are all 0. Okay. Right? Therefore, this will be the general solution. It's a particular case. Okay. So I hope you have understood the general technique. Do you have any questions on this? Have you understood the general method?
Yes, sir.
Okay. Right. So now I can take up. Then I can take. Now I can take up general higher order equations. So we will start with that. We now work with the following. General Let us write down the general nth order linear equation. is given by this is the general nth order linear equation. It's not homogeneous. It is homogeneous if Qt is identically equal to 0. Now, what we have is, see, we have developed a theory for this system. Recall, this is the system that we have used, and the leading coefficient here is 1. Okay. So, what I do is, I make an assumption here that P naught T is not equal to 0. This is for T1 less than T, for T then what I can do is I can divide this by P naught and rewrite the whole equation in the form I use the same Pi. Okay, so let me write now. I have used the same Pi to designate. In the earlier version I had P1, P2, etc., Pn and Q. I divide each one of this by P naught and rewrite those functions again by P1, P2, etc., Pn. So don't get confused at all. Okay, right? Or in other words, I am just assuming P naught is identically equal to 1. Okay, so let me put it that way. Why I do that? That will be clear soon. Because any 0 of the leading coefficient a singular points. And the existence and uniqueness theorem is not valid in a neighborhood of that. I'll make this point clear. For instance, you look at this equation. Something like this. Just one variable case. Now you recall how have we developed the theory, the general theorems for this. See, we have considered this equation dx by dt equal to f of xt. Okay. So if you rework this equation into this form, what you have to do? You have to divide by P naught t. So assume P naught t vanishes nowhere. Okay, assume P naught t vanishes nowhere. Then what you have? You can write this in the form dx by dt equal plus q by P naught. If P naught does not vanish anywhere on the interval, then you see that P1 by P naught and Q by P naught are continuous functions, and you can write in this case what dx by dt is equal to f of xt, where f of xt will be continuous with respect to the variables x and t. Otherwise, what happens is that these functions would fail to be continuous at the zeros of the leading coefficient. And you cannot apply the theory that you have developed here, because you see they are going to come up as singular points. It's the same story when you consider the higher order equation. Therefore, we take the equation in this particular form. This is what is called the normalized equation. I will write this here. One is called the nth order linear equation, linear differential equation in the normalized form. So we take it in the normalized form in the sense that the leading coefficient or the leading coefficient is equal to 1. That is the coefficient of the highest order of derivative of the unknown is taken as identically equal to 1. That is the you can always reduce this to this form provided P naught t does not vanish anywhere on the interval, because you can divide by that and redefine the equation. So this is the standard form in which we take this, where for this equation we show that invoke the existence and uniqueness theorem. So that's what we try to do. Oh. Okay. Now what we do is this, the following. Okay, I will continue with the stock at 12 o'clock. Okay, right. So make an exit.